Hello everybody, welcome into another lesson. So today we are going to talk about reflections. Let me get my book here, that might help. So we are going to talk about reflections, which reflections you could think of it like looking in a mirror. If you look in the mirror, you see your reflection. If I put this board in a mirror, I'm going to see the reflection of the board. A reflection is also in isometry because it does not change the size of the object. It does not change the size at all. So a reflection is in isometry. It preserves the distance, it preserves length, area, volume, what have you. First thing we're going to talk about is a reflection in the x-axis. So of course you have your x-axis here. Think of the x-axis like a mirror. So if I reflect this with this point A, which is at 4, 5 in the mirror, I'm using the x-axis as a mirror. And to use the x-axis as a mirror, you'll take your preimage, your point you're starting with, and what you're going to do is keep your x-coordinate the same, but negate your y-coordinate. So it would go from xy to x negative y for a reflection in the x-axis, because you're using this horizontal axis as the mirror. So if I want to find a prime, which would be the reflection in the x-axis of 4, 5, all I'm going to, actually that's negative 4, 5, excuse me, I had it wrong. There I go, starting again already. So there's A at negative 4, 5. If I want to reflect this in the x-axis, I'm going to keep my x-coordinate the same, but negate my y-coordinate. So if I negate that 5, I would be at the point 4, negative 5. So you would get A prime at the point negative 4, negative 5. So all I've done to reflect this in the x-axis is just negate the y-coordinate. So A prime would be at negative 4, negative 5. And I got a few more points to illustrate here, to illustrate a reflection in the x-axis. Okay. What does point B have? Point B is located at 2, 4. So I have point B, which is located at the coordinate 2, 4. Again, I want to reflect B in the x-axis, right? I'm using the x-axis as a mirror, so if I do that, I'm not going to change my x-coordinate. That's going to stay at 2, but my y-coordinate will change. If I negate the y-coordinate of 4, that will put me at 2, negative 4. So B prime, which would be the transformation, would be at 2, negative 4 if I'm reflecting this in the x-axis. Alright, let's do a point C. Now point C is different. That is located at 5, negative 1. So we have point C, which is located at 5, negative 1. Well, we need to find C prime, which would be a reflection in the x-axis. If I want to reflect this in the x-axis, I keep my x-coordinate the same, but negate my y-coordinate. What's negative, negative 1? That'd be positive 1. So my C prime would be at the point 5, positive 1. That's where my C prime would be located, at the point 5, positive 1. Do a few more so we can drill down the x-axis here. Then we'll go to reflections in the y-axis. Alright, point D is at the point 0, 5. So point D can be found at the coordinate 0, 5. we want to find d prime. So we have it right on the y-axis, but that's no worry. We want to reflect this in the x-axis. Using the x-axis as a mirror, we keep the x-coordinate the same but negate the y-coordinate. If I negate the 5, I would be at a point of 0, -5 for my d prime. So d prime would be at the coordinate 0, -5. There it is. Looking for my black marker. Alright, let's look for point E. Point E would be at 6, 3. Whoops, I wanted to make that red. Excuse me. Excuse me a minute. So point E would be located at the coordinate 6, 3. I want to take E and find E prime by reflecting this in the x-axis. So to do that, I am going to just negate my y-coordinate but keep my x-coordinate the same. Well, this would put me at 6, -3, which would be right about there. So E prime would be found at the coordinate 6, -3. So you see how this demonstrates reflection in the x-axis? You're using the x-axis as a mirror. So that's why you negate your y-coordinate and leave your x-coordinate alone. I got one more point for the x-axis, then we'll go on to the y-axis. Alright, point F is going to be at -3, 1. So we have point F at the point -3, 1. We want to find F prime, which will be a reflection in the x-axis. So to reflect in the x-axis, I'll leave my x-coordinate of -3 alone, but I'll negate that 1 for the y. Well, this would put me at -3, -1 for F prime. So F prime has the coordinate -3, -1, since it's a reflection in the x-axis. Alright, so we have seen reflections in the x-axis, which use the x-axis as a mirror. Now, what we are going to do is we're going to reflect in the y-axis. So this time we will use the y-axis as a mirror. So there's also types of reflections where you use the y-axis as a mirror, the standing straight up and down, which in real life the mirror's not laying down on the floor. In real life it's standing straight up and down. So I would say the reflection of the y-axis really imitates real life a lot more clearly. So we're going to do some of the same points again, but we're going to reflect in the y-axis. To do a reflection in the y-axis, since the y-axis stands straight up, you have your xy coordinate of the original. This time you negate your x coordinate, but you leave your y coordinate alone. So to find the reflection in the y-axis, you negate your x coordinate, but you leave your y coordinate alone. So you will get the coordinate -x, y. So this time we have A located at -4, 5, right? We want to find A prime by reflecting this in the y-axis. To reflect in the y-axis, you'll negate your x-coordinate, so -4 is +4, but you leave your y-coordinate alone. which means my A prime would be at the coordinate positive 4, 5. So you see that reflection in the y-axis using this as a mirror. I've negated my x-coordinate, but I've left my y-coordinate intact. I've left it alone. That doesn't change it. Alright, let's do a few more points here. What about point B, which is found at 2, 4? So my point B is at the point 2, 4. I want to find B prime by reflecting in the y-axis. Again, to reflect in the y-axis, I negate my x-coordinate, which would put me at -2, but I leave my y-coordinate of 4 alone. So I would be at the coordinate -2, 4 for B prime. So B prime has a coordinate of -2, 4. And again, you see that reflection in the y-axis. I've only changed the x-coordinate, but I've left the y alone. Okay, let's do a point C. Point C is at 5, -1. So C can be found at the point 5, -1. I want to find C prime by reflecting this in the y-axis. Again, to reflect in the y-axis, I take the negative of my x-coordinate, so negative of 5 would be at -5. By leaving my y-coordinate of -1 alone, I would be at the point -5, -1 for C prime. If I am reflecting this in the y-axis, C prime is at -5, -1. All right, let's do a point D. So point D can be found at 0, 5. And this is a good one. Point D is at 0, 5. This time, though, I want to find D prime by reflecting it in the y-axis. So, to find D prime, I'm going to take the negative of my x-coordinate. Well, negative of 0 is also 0, right? But you're still leaving the y-coordinate alone. Well, you go nowhere. You can have cases, if it rests right on the axis, where D and D prime are the same coordinate. So there's literally no change. D and D prime are one and the same at 0, 5 in this case. All right, let's go for point E, which would be at 6, 3. So point E is located at the coordinate 6, 3. I want to find E prime by reflecting it in the y-axis. So again, to reflect in the y-axis, I'll negate my x-coordinate of 6, which would actually put me at -6, but I leave the y-coordinate of 3 alone, which means I would get a coordinate of E prime at the coordinate -6, 3. So E prime would be located at -6, 3 if I'm reflecting it in the y-axis. Alright, one last point with this, then there's another type of reflection we're going to talk about. So let's see, a point F would be at -3, 1. Whoops. So we have point F located at -3, 1. I want to find F prime by reflecting this in the y-axis. So if I want to find f prime by reflecting in the y-axis, I take my x-coordinate of -3 and negate that, so -3 is +3. Then I leave my y-coordinate alone, so that means my f prime would have the coordinate of +3, 1. And again, you see the symmetry in the y-axis. So that's how we just negate the x and leave the y alone. Now there's another type, another common type when you're dealing with the coordinate plane. There are other types too, but we're not going to talk as much at length, but we'll talk about another type here. So there's also a reflection in the line y = x. Alright, so in fact, let me go ahead and draw the line y = x. Let me draw a little dotted line to illustrate this. Okay, so there's my dotted line for y = x. That is actually another type of symmetry. So, if you want to reflect in the line y = x, which is the third most common type, you have your original image, which is at xy. You just take, to get the reflection of the line y = x, you literally just take your x and y coordinates and switch them around. So it'd become yx. You just switch the two around. So let's do this again. You have A at -4, 5. You have a point A which is located at -4, 5. We want to find A prime by reflecting it in the line y = x. To do so, you're just going to take your x and y coordinates, switch places with them. To find A prime, you would end up with 5, -4. So A prime would be at 5, -4, since you just switch your x and y coordinates around. And you can see how you can use y = x as a mirror. You see how they're diagonal from each other. You should always get a diagonal. If you draw a line, you would get a diagonal line. So, that's a very interesting reflection. Let's do a point B. Point B would be located at the point 2, 4. So B itself is at 2, 4. Alright, so if we want to find B prime, we just need to take the x and y coordinates and switch them around. If we do that, well, you would get B prime located at 4, 2. So if you reflect B in the line y = x, you would get B prime at 4, 2, since you're just switching your x and y coordinates around. Alright, now let's see, let's do a point C. Point C is at 5, -1, okay? So we will have point C at 5, -1. If we want to find C prime by reflecting in the line y = x, we just got to take our x and y coordinates, switch them around. You would be at the point -1, 5, which would put you all the way up here. So C prime can be found at the point -1, 5 if you reflect in the line y = x. Alright, let's do a point D. Point D is, again, at the point 0, 5. So point D has the coordinate 0, 5. We want to find D prime by reflecting this in the line y equals x. So we'll just switch the x and y coordinates around. Well, if you wanted to find D prime, that would put you at the point 5, 0. And again, you see the symmetry between x and y. In fact, if you were to connect D and D prime, make a line segment, we're going to cover this in a few minutes, you would find that that line segment is perpendicular to the line of symmetry. It's perpendicular to that line of symmetry. That's what it's called. So that line y equals x is the line of symmetry. It preserves distance from each point. It's halfway between the points. And the line that goes through the points is perpendicular to your line of symmetry. Okay, let's do a point E, and then we'll do a point F, and then we'll move on. Let's just reconnect these axes here, all right. Whoops, I knew I forgot something. All right, let's do a point E. So point E can be found at 6, 3. So there's E located at the coordinate 6, 3. If we want to find E prime, again, just take your x and y coordinates, switch them around. You would be at the point 3, 6. So E prime would just put you at the point 3, 6. If you reflect it in the line y equals x, you would be at 3, 6 for E prime. All right, let's do a point F. Let's do a point F. Point F is located at negative 3, 1. So negative 3, 1 is your point F. Now, to, of course, find F prime with your line of symmetry being y equals x, you just switch your x and y coordinates around, you would be at 1, negative 3. So F prime would be located at 1, negative 3 for that point. All right. So there is that. Now let's talk about some other things here with reflections. I think reflections are actually pretty cool. So here's what we're going to do. Alright, so in general, we can really use any arbitrary line as a mirror, as a reflection. So, or a line of symmetry. If that's a line of reflection, it's a line of symmetry. So, we're going to talk about reflections and lines in general, even if they're not on the coordinate plane. If I reflect something in line K, right, this red line is line K. Wouldn't that function as like the x-axis since it's horizontal? It would function kind of like your x-axis. This blue line J would function kind of as your y-axis, standing straight up. So let's say I wanted to find, let's see, find the reflection in line K for point A. I'm being asked to find the reflection in line K for point A. There's a way I can actually abbreviate that. I can totally abbreviate that. You know how? Here's how. If I abbreviated uppercase R with a lowercase subscript k, that means reflection in line K, and then I put a colon for A. So this denotes a reflection in the line K at point A. And of course, what would be the value of that if I actually were to take the reflection in the line K at point A? What would that be? If you reflect in the line K at point A, since K, of course, is a horizontal line, you're not shifting any further left or right, you're just shifting down. That would be the point D. That would be the reflection in the line K at point A, would just be point D, since line K lays straight down. So we're going to do a few of these exercises here in general to get you used to what you might see in some books for reflection notation. So what if I'm asked for, this time, the reflection in line K, you also may see comma, instead of colon, you may see parenthesis B. So you could either see it one of two ways. You could see it as R sub K parenthesis B or R sub K colon B. You could see it either way. They both mean the same thing. These mean the reflection in line K at point B, which would be, of course, C. Since we're reflecting on a horizontal line, that would just be point C, would be the reflection through line K at point B. Alright, so then what if I had... You can also not only do this with points, you can do this with whole segments. What if I'm asked to find the reflection in line K of the segment AB? Well, again, if it's in line K, it's a horizontal line, so I'm just going to go straight down. That would be at the segment DC or CD, however you prefer to say it. You could list it either way, CD or DC, it doesn't matter, but line segment CD would be the reflection in line K of the segment AB. Alright. Now, what if I'm asked to do the reflection in K of the point C? So I'm being asked to find the reflection through the line K at point C. Well, if I'm starting down, that means I'm going up, right? Since this is a horizontal line, the reflection through K of C would be actually at point B in this case. So point B would be the reflection of C through the line K. All right. Now, what if I were asked to find a little bit different? The reflection in K of point T. So now we've shifted to this one here. Well, that's point S. I suppose I should say that. There we go. What if I'm asked to find the reflection in line K of point T? Well, T is right on your line of symmetry, right? If it's right on the line of symmetry, there's nowhere to shift it to, because a line of symmetry preserves distance and length. So if it's on the line of symmetry, it's going to be at point T itself. That would be the reflection through line K at point T would be point T itself. All right. So the reflection in line K of the segment BC. We want to find the reflection in line K of the segment BC. Well, if you're going to look for BC, find it in line K, there really is no change. You know why? Because this is a horizontal line. Now the reflection of B would be C, the reflection of C would be B. So you're really not making any changes from left to right, you're just changing up to down. If you're reflecting through K, since it's a horizontal line, so the reflection through K of the segment BC would be the segment BC itself. That's what you would get, the segment BC itself. All right. Now here's another one. What if I reflect through the line K of angle STU? I'm going to reflect through the angle K of STU. Well, it's going to be the same angle, but technically we're going to write it a little bit differently. Because the point T, which would be the vertex of the angle, since the vertex of the angle is always in the center of the name, that doesn't change, but the reflection from in line K from S to U is U, and the reflection from U through line K is S. So this would actually be angle UTS, which would still be the same angle, it's just listed in a different order. You would get angle UTS. I think we're ready for some line J's. Very good. So this time we're reflecting through the line J of the point S. We want to reflect through the line J of the point S. All right. Now, J is a vertical line, right? That would pretty much, you could think of that like your y-axis, a vertical line. So that means you would negate your x-coordinate, but you keep your y-coordinate the same. So if you reflect through line J from point S, that would give you the point W. So the answer you would get would be the point W for a reflection through line J for point S. All right. Let's see here. A few more of these. Actually, we'll do two more of these. The reflection through line J of the segment ST. So we are going to reflect through the line J of the segment ST. Well, again, this is your horizontal axis is what J functions as, so your y coordinates don't change, but your x sure do. What fits the bill here would be WX. You would get line segment WX. That would be the answer. Since it's a reflection through the J, line J, you would get WX for the reflection. Now one more. Just one more for these. Alright, let's say the reflection through J, this time we don't know, is the line segment XY. So we don't know what's reflected through line J to give you a line segment of XY. Okay, so this is basically working backwards. What would give you an image of XY if it's reflected through line J? Well, again, so if you're reflecting through the vertical axis, you're not changing your y coordinates at all. You're only changing your x coordinates. Well, that would be TU. So that question mark would actually be the line segment TU. That would be the reflection in the line J of XY. You would get the line segment TU. All right. We're going to do about 6 more exercises here, but these are different. I'm only going to graph the first one, though, because I wish to illustrate a point. We are going to graph the first one. So, and then we'll just simply do these equations afterwards. Okay, so here's what we're going to be asked to do. So we are given that we have some arbitrary line K that we're reflecting to. So the reflection through line K of A is A prime. Find the equation of line K, which would be your line of symmetry. That would be your line K, your line of symmetry. So here's how we're going to do this. So we are given that point A has the point, in this case, 5, 0, and then we have that A prime has the point 9, 0. So the reflection through line K of point A at 5, 0 is A prime at 9, 0. We need to find the equation of that line K. If it helps us first, why don't we plot the points? Let's plot the points here, right? So let's go to 5, 0. There's your A, which is located at 5, 0. Let's find A prime, which is located at 9, 0. All right, so there is your, there is your A and A prime. So how are we going to find the equation? How do we do that? Well, I'll tell you exactly how you do it. To begin with, you need to first picture that A and A prime form a line segment, that they're connected to each other. So I'm going to draw in purple to connect these two. Now we have a line segment going from A to A prime. So now that you've formed your line segment, we need to find the slope. So let's go ahead and find the slope of the line segment A prime. Well, of course, to find the slope, we'll take the y2 of 0 minus your y1 of 0 over your x2 of 9 minus your x1 of 5. Well, that'd be 0 over 4, which would give you 0. Your slope is 0, right? Okay. That's great. So we found the slope to be 0. Now, we also, a line of symmetry, think about it. What does it do? It preserves the distance between the points. If we've noticed, it's always halfway between the 2 points. It would be halfway between A and A prime. So what do we need to find? We actually need to find the midpoint of A prime. So to find the midpoint, of course, that'll be equal to your x1 of 5 plus your x2 of 9 over 2, and then your y1 of 0 plus your y2 of also 0 all over 2, which would end up giving you 14 over 2, 0 over 2, which would now give you a midpoint of 7/2. Whoops, 7/2, it'd be 7/0. I don't know what I'm saying. Ignore that. So the midpoint is at 7/2. So let's draw that midpoint here. The midpoint can be found at the point 7/2. Well, heck, if you want, call that point M. That's fine. M's the midpoint, which would be at 7/0. Right? Okay. Now, we're almost there. We just got to find the equation. Whenever you find the equation, you want to consider the perpendicular bisector of the segment. So consider the perpendicular bisector of the segment. And I'll show you more in a second why it's a perpendicular bisector. But if it's the perpendicular bisector, one thing that's true is the line is perpendicular to your line segment. If we were to have a perpendicular line to the slope of A prime, it would have to be the negative reciprocal of 0, which would make this what? An undefined slope. It would be an undefined slope, which means what? That you're going to have the equation x equals, which would give you a vertical line. So if you have an undefined slope, then x equals, that means the equation of the line would simply be x equals 7. Now, if you want, we can draw that line, x equals 7. All right, so there's your line of symmetry through x equals 7. Okay, and then if we notice 5, 0 and 9, 0 are both equal distant to that line of symmetry and each other. And you notice too, there was only a change in your x length and not your y length. So this line x equals 7 would almost function as your y-axis. It would function the same way since it's a vertical line. So this proves that you can have symmetry in other lines, and that the line of symmetry will always be perpendicular. It'll be the perpendicular bisector actually of the segments of the segment that joins your A and A prime. So I got more examples here, but I just wanted to show you one example with graphing. Now we'll just simply worry about the equations. Because a lot of the time you're not going to be asked to graph it. I just wanted to explain what was going on to help you understand it. Alright, so let's say this time you have a point A. You have a point A that is at the point 1, 4. And then you have an A prime that is at the point 3, 4. Okay, so the reflection through line K at point A being 1, 4 yields the point A prime of 3, 4. We need to find the equation of that line K, that line of symmetry. So first, find the slope of the line segment that joins A prime. So let's go ahead and let's do that. The slope of the line that would join A prime, of course, take your y2 of 4 minus your y1 of 4 over your x2 of 3 minus your x1 of 3. Well, 4 minus 4 is 0 over 2. That's just going to give you 0. You get a 0 slope. Alright, next, since you found the slope of the line segment that joins A and A prime, go ahead and find the midpoint of this segment. So let's find the midpoint. Actually, let me write in green. I kind of want to separate these. So the midpoint of the segment is going to equal, you take your x1 and x2 of 1 plus 3, divide that by 2, and then take your y1 of 4 plus your y2 of 4, divide that by 2. So that's going to yield a midpoint of 4 over 2, 8 over 2, which would ultimately turn your midpoint into 2, 4. The midpoint of this segment is at 2, 4, which means the perpendicular bisector of that segment has to pass through the point 2, 4. And of course, if we're going to find the slope of the perpendicular bisector, again, it's the negative reciprocal of the line segment that joins A to A prime. The negative reciprocal of 0 is an undefined slope, which means you're going to get x equals. You just get the equation x equals, which in this case would be 2. So the equation for the line of symmetry in this case would be x equals 2 for the line K. I got 4 more. Alright, let's do you have an A at 4, 0. You have an A prime at the point 4, 6. So the reflection through line K of point A at 4, 0 yields the A prime of 4, 6. We need to find the equation of that line K. So first, let's find the slope of the line segment that joins A prime. So if we are to find the slope of the line segment A prime, I should probably put a segment notation above it. You'll take your x2 of 6, sorry, your y2 of 6 minus your y1 of 0 over your x2 of 4 minus your x1 of 4, which would end up giving you 6 over 0 is undefined. So you have an undefined slope for the line segment that joins A prime, which would actually be a vertical line at this time. Now that we know the slope, let's find the midpoint of the segment that joins A prime. So let's go ahead and find the midpoint. The midpoint, of course, would be found at your x1 of 4 plus your x2 of 4 divided by 2, and then you'll take your y1 of 0 plus your y2 of 6, divide that by 2, which would give you, of course, 8 over 2 for your x-coordinate, 6 over 2 for your y-coordinate, giving you a total midpoint of 4, 3. So the midpoint of this line segment would be 4, 3. And again, what do we know about the equation of line K, the line of symmetry? It's the perpendicular bisector of the segment A prime. So, of course, let's start with the slope of what the line would be of the perpendicular bisector. If the original line is undefined, the negative reciprocal of that is 0. So you'll actually get a slope of 0. If you remember the Hoy acronym, you would get a horizontal line, 0 slope, y equals. So take y equals 3. Y would equal your coordinate of 3. So the line of symmetry can be found at y equals 3. And I got 3 more. Alright, what if we have the point A is going to be at the point 5, 1. A prime would be at the point 1, 5. So we have the reflection through K of point A is 5, 1. The reflection through K at point A being 5, 1 yields A prime being 1, 5. Of course, find the slope of the line segment that joins those 2 points. So take your slope of that line segment A prime. That's going to give you, of course, y2 of 5 minus your y1 of 1 over your x2 of 1 minus your x1 of 5. Well, that's going to give you, of course, 4 over negative 4, which is going to give you negative 1. So you have a slope of negative 1 for the line. Now, of course, let's go ahead and, once we found the slope, let's find the midpoint of those 2 points, because the perpendicular bisector runs through there. Whoops, wrong color for the midpoint. Let's find the midpoint. The midpoint would, of course, be equal to your x1 of 5 plus your x2 of 1, divide that result by 2, and then you'll take your y1 of 1 plus your y2 of 5, divide that result by 2, which would end up giving you 6 over 2, comma 6 over 2, which would give you a midpoint of 3, 3. So the midpoint of the line segment is at 3, 3. So now we need to go ahead and find the perpendicular bisector. So, alright, what would be the slope of the perpendicular bisector for the line segment? In other words, what's the negative reciprocal of negative 1? Wouldn't that be positive 1? That would be that's the negative reciprocal of negative 1, would give you positive 1. So the slope of the perpendicular bisector would end up being 1. Now to find the equation of the line of symmetry, you just take the coordinates of your midpoint of that segment and you put them into point slope form. So take your y minus your y1 of 3, set that equal to your slope of 1 times your x minus the x coordinate of 3. So you're taking the slope of the perpendicular line and the coordinates of the midpoint and putting that into point slope form. Well, this would just give you y minus 3 equals x minus 3, which, what do you know, would give you y equals x. So the line of symmetry in this case is y equals x. Or you could have saved yourself all that trouble if you remembered that in the reflection of the line y equals x, you just reverse your x and y coordinates. You could have found it that way too, but this is a longer way to find it, y equals x in the end. 2 more problems, then we're done. All right, what do we got now? All right, this changes again. I want the red marker. So A is at the point 0, 2. A prime is going to be located at the point 4, 6. So we have the reflection through line K at point A being 0, 2 yields A prime at the point 4, 6. So first thing, of course, find the slope of the segment that joins them. So to find the slope of line segment A prime, take your y2 of 6 minus your y1 of 2 over your over your x1 of 4, or your x2 of 4 minus your x1 of 0. Well, this would just give you 4 over 4, which would give you a slope of 1. So the slope of the line segment that joins AA prime is 1. Now that we found the slope, find the midpoint of the segment. So to find the midpoint again, we'll put in the midpoint formula. So x1 is 0 plus your x2 is 4. Divide that by 2, and then take your y1 of 2 plus your y2 of 6, divide that by 2, which would end up giving you 4 over 2, 8 over 2, which would end up giving you a midpoint of 2, 4. So the midpoint of that segment is located at the coordinate 2, 4. Now, last but not least, we need to find the equation of that line of symmetry, but we know this line of symmetry is the perpendicular bisector to the segment that joins those 2 points. So, if the line's supposed to be perpendicular to the segment, the negative reciprocal of a slope of 1 would be negative 1. So the slope would actually be negative 1 for the perpendicular bisector. So take that slope and then the midpoint and put those into the point slope form of the equation. So take your y minus 4, set that equal to negative 1 times x minus 2, which would end up giving you y minus 4 equals negative x plus 2, which would then give you that y equals negative x plus 6. So the line of symmetry in this case is going to be at the line y equals negative x plus 6. So this is starting to prove that you can have lines of symmetry in all kinds of other lines. All right, one more and then we're done for the day. One more and we are done for the day. So A is found at the point negative 1, 2. And then we have A prime, which is going to be found at the point 4, 5. So this tells you here that the reflection through line K at point A being negative 1, 2 yields A prime of 4, 5. So first thing, find the slope of the line segment AA prime. So the slope of that line segment, of course, take your y2 of 5 minus your y1 of 2, over your x2 of 4 minus your x1 of -1, which would give you 5 minus 2 over 4 plus 1, which would just turn into 3/5. So the slope of the line segment would end up being 3/5, right? Okay. So we found the slope. Now we need to work on finding the midpoint of that segment. So find the midpoint. That, of course, is going to end up equaling your x1 coordinate of -1 plus your x2 coordinate of 4, all that divided by 2, and then you'll take your y1 coordinate of 2 plus your y2 coordinate of 5, dividing that by 2, which would end up giving you a midpoint of 3/2, 7/2, which that's perfectly normal to have fractional midpoints. So the midpoint of this line segment will be 3/2, 7/2. Now, we found the slope of the line segment, we found the midpoint of it, and we know that the line of symmetry is the perpendicular bisector of that line segment. So we need to find the slope of the perpendicular bisector. So what's the negative reciprocal of 3/5? That'd be -5/3. So the slope of the perpendicular bisector would be -5/3. Now just put those coordinates of the midpoint into your slope-intercept form. So take y minus that y1 of 7/2, and then you would equal that times your slope times your x minus your x1 of 3/2. So this is starting to look a little bit like a doozy, but it's not that bad. So this would turn into y minus 7/2 equals -5/3 x plus 15/6. Right? So now we need to add 7/2 to this side. So you would get y equals -5/3 x. All right, so if 15/6 plus 7/2, wouldn't that be the same as 21/6? You would end up getting -5/3 plus 36/6, which would simply turn this into y equals -5/3 x plus 6. So the equation of the line of symmetry in this case would be y equals -5/3 x plus 6. So that's it for reflections. We are down to 3 more lessons in this unit and in geometry in general. The next lesson we will talk about translations and glide reflections. So I hope everyone has a great night. Take care.